All right, welcome. Today, we're going to tackle a classic coding interview problem that's all about graph traversal, how to find the shortest path in a binary matrix. So let's dive right in. You know, when you really boil it down, this problem is just like finding the fastest way out of a maze. You've got a start, an end, some open paths, and some walls. The goal? Find the route with the fewest steps. Simple as that.
So to put it a bit more formally, what we're given is this square grid. Our job is to get from the top left corner all the way to the bottom right corner, and we need to find the absolute shortest clear path to do it.
Okay, so this is what it looks like in practice. This grid is our maze. Think of the zeros as your open hallways, and the ones, those are solid walls you just can't go through. And you can see our mission, get from that highlighted start cell to the end cell.
Now, every game has rules, and here are ours. First, we've got a pretty cool power. We can move in 8 directions, kind of like a king on a chessboard. So diagonals are totally fair game. Of course, we can only step on those open 0 cells. And the length of our path? It's just the number of cells we step on. Finally, if there's just no way to get to the end, we have to report that by returning -1.
So this brings up the big question, right? Every single step we take costs exactly the same. It's just one move. With that in mind, what's the best algorithm to guarantee we find the shortest path and not just some random longer path?
And the answer, hands down, is breadth first search, or BFS. The best way to think about it is like dropping a pebble in a pond. BFS explores the grid in these expanding ripples. It checks all possible paths that are 1 step away, then all paths that are 2 steps away, and so on. This ripple effect guarantees that the very first time we hit that destination cell, it has to be via the shortest possible route.
Okay, before we even think about writing code, we need a solid game plan. Here's our 4-step approach. First, we'll check for any obvious dead ends right from the start. Second, we'll set up our queue with the starting position. Third, we'll kick off our main traversal loop. And fourth, inside that loop, we'll explore all the valid neighbors and add them to our queue.
First things first, let's get the easy stuff out of the way. If our starting cell is a wall, or if the destination cell is blocked, well, a path is just not going to happen. So we can immediately return -1 and call it a day.
Next up is the setup. We're going to use a queue which, works just like a line at the grocery store. First in, first out. We'll add our starting point to it, that's row 0, column 0, with a distance of 1 since we're starting on it. Now listen, this next part is super important. We immediately mark that starting cell as visited. Why? This stops us from accidentally coming back to it later and getting stuck in an endless loop.
All right, now we're ready to get things moving with our main loop. As long as there's something in our queue to explore, we'll pull the next cell out from the front. We'll grab its row, its column, and the distance it took to get there. And the very first thing we do is ask, are we there yet? If our current coordinates match the end of the maze, boom, we found it. That's the shortest path, so we just return the distance.
Okay, so from our current spot, we need to look around at our neighbors. This is a really slick way to check all 8 directions without writing a ton of if statements. These nested loops, using max and min, are a clever trick to make sure we never try to look outside the boundaries of our grid. And for each of those neighbors, we just check one simple thing. Is this an open path? Is it a 0? If the answer is yes, then it's a valid place to go. So we do 2 things. We immediately mark it as visited so we don't check it again, and then we add it to the back of our queue with a distance that's just 1 step more than where we came from.
But what if the loop finishes? Well, that means our queue is totally empty. We've explored every single possible path from the start, and we never ever reach the destination. That's how we know for sure that no path exists. So in this case, we return -1.
So how does this all stack up performance-wise? It's actually really efficient. In the worst-case scenario, we're going to visit every single cell in our n-by-n grid exactly 1 time. That gives us a time complexity of O of n squared. And our space complexity is also O of n squared, because in the worst case, our queue might have to hold on to most of those cells at once. All right, so let's wrap this up. What are the big takeaways here? Well, first, if you see a problem that says shortest path, and every step has the same cost, BFS should be screaming in your head. Your main tool is the queue, and the absolute most important trick is to mark what you've been to avoid going in circles. And of course, always check for those simple edge cases first. It can save you a whole lot of trouble.
And there you have it. That's our solution. But solving one problem usually just opens up another one. What if moving diagonally costs more than moving straight? Suddenly, our BFS approach wouldn't work anymore because not all steps are equal. So what algorithm would you use them? Something to chew on for next time, right?